Welcome back to 2008X. I'm Professor John Hart from MIT, and today we'll focus on additive manufacturing, which you may also know as 3D printing. Now, even if you've never used a 3D printer or designed a part for additive manufacturing, you know that this represents a very important technology to manufacturing now and more so in the future. And we can see many examples of this importance based on what industry is doing with additive manufacturing. For example, GE starting to print parts out of metal for their jet engines, Google thinking about deploying modular products such as smartphones where the cases are made using 3D printing. Doctors printing custom parts to save people's lives using 3D printing, and consumer products companies such as Nike thinking about making custom personalized shoe soles. We'll get back to these examples later on, but you may have also heard that 3D printing was invented at MIT, and that, in terms of one particular process that's still used today, is in fact true. This is a photo of one of the first parts made on MIT's 3D printer, made about 25 years ago. At that time, Professors Ali Sachs and Michael Sema and colleagues invented the 3D printing technology, which involved building parts up layer by layer from a powder-based material, where the powder was glued together using an inkjet printing technology. Now, this is a small model of the Hagia Sophia, a famous landmark in Istanbul, Turkey, and you can see the fine level of detail they achieved, and also that the part has hollow internal cavities. That's one of the hallmarks of the flexibility of 3D printing, and that was seen and demonstrated in this part. In fact, I have one of the several remaining parts that floats around various offices at MIT here in my hand, and we can see it under the camera. And by looking at the top surface of a part, you get the sense of the fine degree of texture as well as the granularity. That's both a strength and a weakness of 3D printing overall. And if I turn it at an angle, you see the tall, thin features that could be created, as well as the layers from the side, the staircasing of the side of the part, and the internal cavities that I mentioned before. So this immense flexibility in geometry, as well as the limitation in the resolution and level of detail, is an important attribute when comparing and contrasting what additive manufacturing can do compared to conventional manufacturing. As you might expect, the inventors of 3D printing at MIT received a patent. Their patent was granted in 1995 and filed several years earlier, and their patent is in fact entitled Three-Dimensional Printing Techniques. Here's a basic schematic of the process where powder is spread inside a build tray, which we sometimes call a powder bed, and after each layer of powder is spread, an inkjet deposition system deposits a liquid that binds the powder together in the areas where the part is to be formed, thereby taking each consecutive layer of the part and binding together those areas that you want to remain and built into the 3D geometry. You perform 3D printing. And they received quite general claims for their technology, and this 3D printing technology led to several successful entrepreneurial efforts. If you come to Cambridge and you visit the MIT Museum, you have the chance to see this printer. This is one of the original 3D printers on which parts like we showed were made. And in some ways it's similar to 3D printers today. It contains the printing mechanism. Here's the powder bed in the inkjet printer. It contains a computer for controlling the process. Then it contains a lot of electronics for communicating the instructions to the printer itself. But of course, the component technologies have advanced a lot since then. And while we're very proud at MIT that 3D printing was invented here, and it was important to the early growth of this industry, there are a lot of other examples of early additive manufacturing or 3D printing. For example, about 10 years earlier than that part at MIT was made, a fellow in Japan named Kodama invented the first 3D photopolymerization process, analogous to what we today call stereolithography. He took a photocurable polymer, one that can harden when exposed to light, and layer-wise stacked up layers with different cross-sections and made parts such as this small house model made by his process. Now, it's quite poor in its level of detail and accuracy, but it demonstrated the basic concept. Another popular printing technology, particularly for metals, is what's called selective laser sintering or selective laser melting. And that has advanced rapidly only in the recent few years. But as early as 1979, researchers were thinking about this. In fact, not a researcher, but a gentleman in Las Vegas, Nevada in the US, named Ross Householder, got the first patent on what looks similar to laser sintering today. The story is he would drive to work through the desert outside of Las Vegas every day, and he would look out the window of his car and he saw the sun shining down on the sand of the desert. And he had the idea that he could build parts in 3D by this process. So he filed a patent, he was granted that patent, and then demonstrated the process not using a laser but just by forming consecutive layers of sand. And then he moved on to other things in his career, but his patent was licensed by researchers who started the first metal 3D printing company about 10 years later. And that company was founded by faculty at the University of Texas at Austin. So like in many industries, we see early innovations, and then we recognize the time it takes for the technology to really come to fruition and have mass market impact. And that's why we're so excited about additive manufacturing today. And all of these processes taken together subscribe to one key difference. In previous lectures, particularly on machining, we talked about material removal, what we might call a top-down process. Here in CNC machining, we of course start with a bulk workpiece and we remove the material needed to create our final part. That contrasts additive manufacturing, which is intrinsically a bottom-up process. We're able to build up materials into free-form geometries into the parts that we want one layer at a time. And by adding material from the bottom up, layer by layer, as seen in this simple desktop 3D printer, which uses polymer extrusion, we can build a great variety of geometries, and we generally don't have to have tooling like we do in processes such as injection molding. So appreciating these differences, the advantages and disadvantages, and where they stand today and in the future is important to project the impact of additive manufacturing. Now, we probably have a definition of additive manufacturing in our minds already, but to go to the textbook or the standards book, we can say that additive manufacturing refers to a process by which digital 3D design data is used to build up a component in layers by depositing material. That applies to all the processes we've already discussed, and this definition comes from the ASTM Standards Committee on Additive Manufacturing Technologies. This committee has been formed over the past few years to come up with terminology and standards that help grow the industry and let different stakeholders talk to each other on the same terms. And it's okay to call additive manufacturing 3D printing. In fact, it's one of the original processes and that very cool, catchy term that we all use. However, we're starting to say additive manufacturing because we're thinking of the techniques not only for printing or prototyping rapidly, but for possibly making large quantities of parts in the future. And therefore, we say that additive manufacturing is more accurately described as a professional production technique which is clearly distinguished from conventional methods of material removal. So here we are in 2016, thinking about what additive manufacturing can do for us in our careers today and what it will do in the future. So why is it such a big deal now? It's been around for 30 years or more, or at least those key processes were invented so long ago. Well, I think there are many reasons, including those listed here. First, we now have wide access to CAD/CAM software, computer-aided design tools that let us create geometries for 3D printing. We have improved automation and component technologies of 3D printers significantly over the past several years, and their cost has gone down. I'm talking about low-cost motors and mechanical components, as well as things like lasers that drive laser metal printers, for example. We also have a growing library of printable materials, the feedstocks, the filaments, the powders, the photopolymers that go into 3D printers. And in the additive manufacturing industry, we're starting to see many materials companies get into the game because they now see significant business potential. We also have major industry and government investment. Those folks want to encourage the growth of the industry because they see its big applications. And we also see that there's more freedom to operate enabled by patent expirations. Now, many of the original 3D printing companies still survive with great momentum, but a lot of those cornerstone patents have expired, which lets new folks enter and innovate in new ways. And all of these things together, in my opinion, lead to significant momentum and confidence and creative vision. And at the end of the day, I think additive manufacturing is a truly amazing technology. It may be many, many years, if not ever, before we make a majority of what we do by 3D printing, by additive manufacturing, but we don't yet even know the possibilities that it can create. So as we go through this module, here's the chapters we're going to present. First, I'll talk in more detail of what you can actually make using additive manufacturing and why it's so important. Then we'll present an overview of the major additive manufacturing processes, of which there are more than we can address. And we'll talk in detail about three mainstream processes: extrusion additive manufacturing, which you might know as fused deposition modeling, or FDM, photopolymerization, called stereolithography, and powder bed fusion, most commonly referred to as selective laser sintering or selective laser melting. Then I'll briefly talk about just a few of the most exciting emerging additive manufacturing technologies and ways of combining things like electronics with 3D printed parts, and then we'll conclude.